Hello, I welcome you all to your own channel MSK Learnium. In this video, we will solve the problem related to the finite element methods. The problem is for one-dimensional bar element, right? So here the question is for the bar shown in figure, calculate displacement field, stress in each member, reaction at the support. So one bar element is given, means bar member is given to you of having two element. That element 1 is having length is 200 mm and the Young's modulus for this material is 200 gigapascal. Area of this material is 2500 mm square. For the element 2, that length is 200 mm, the Young's modulus is 70 GPa. That area of this element 2 is having 1000 mm square. At this point, you have a 60 kilonewton load is acting. So you know in finite element method, first of all we have to discretize the body. Right, discretization means what? We need to see that how many possible part of element is there, right? So in this member there are the two element. This is element 1 and the element 2, and then we have to locate the nodes. The node is a point where the element can be joined. So this is one node. Here you have a 2 nodes and here you have a 3 nodes, right? Then for each element we will find out the stiffness matrix. For one-dimensional bar element, the stiffness matrix is K is equal to AE by L 1 minus 1 minus 1 1. After finding the stiffness matrix, we will club them, we'll find out the global stiffness and then use the finite element equation, and by elimination approach we will solve the problem. So let's start. First of all, we'll go for the step 1. Okay, so here you have a step 1, right? So in step 1, what we will do, we'll see the finite element model, right? So here we can say finite element model. All right, finite element model. So how many element means in the nodal displacement we will show this is element 1 and this is the element 2. So these are the dotted is your nodes, right? So this is the node 1, node 2 and node 3. This is the element 1 and this is the element 2. All right, then you have a at node 1 the nodal displacement is u1, at node 2 the nodal displacement is u2, and at node 3 the nodal displacement is u3. Okay, so these are the nodal displacement at each element, at each nodes, right? It is one dimensional bar element, so the nodal displacement on one axis only, that is on horizontal, as the body is kept horizontally, right? Then we'll go for the step 2. Next we have a step 2. So step 2 means what? We need to find out the element stiffness matrix, right? So we will see the element stiffness matrix. The element stiffness matrix. Okay, the element stiffness matrix. The element stiffness matrix, stiffness we are denoting by K. So K we will find. So for one dimensional bar element, you can write for one dimensional bar element, right? For one dimensional bar element, that is the stiffness matrix K is equal to A E by L 1 minus 1 minus 1 1. Okay, so this is what you have a formula for one dimensional bar element, a stiffness matrix. A E by L 1 minus 1 minus 1 1. A is the area of the element, E is the Young's modulus and L is the length. Then we will find a stiffness matrix for element 1 and element 2. So here we go, that for element 1, right? For element 1 we can say K1 is equal to A1 by E1 by L1 1 minus 1 minus 1 and 1. All right, so we will substitute the values. That is what A is equal to, for element 1 it is given 2500, Young's modulus is given 70 GPa, right? So you have to take this value into Newton per mm square. Why? Because length we are taken in millimeter, right? So when you take the length in millimeter, so Young's modulus everything will take in the millimeter. Area we have taken millimeter square. So 200 gigapascal means 200 into 10 to the power of 3 Newton per mm square, and the length is 200. And in matrix you have a 1 minus 1 minus 1 1. On simplification, we'll get the value, we can see here, that is 18.75 into 10 to the power of 5, 1 minus 1 minus 1, 1, right? So 18.75 we will multiply, and 10 to the power 5 will take common, right? So this is what 10 to the power 5. So 18.75 is multiplied with 1, then minus 18.75 is multiplied with minus 1, and again minus 18.75, and again 18.75. So this is the stiffness matrix for element 1 we calculated, that is your K1, right? Similarly, we will find out the K2. So similarly, we'll get the K2. So let's see that. So here we go. Now we can write for element 2, right? For element 2. For element 2 is what? That is K2 is equal to A2 E2 by L2, 1 minus 1 minus 1, 1. So directly we'll substitute the value. For element 2, the area is 1000 mm square. Young's modulus is 70 GPa, means it will be 70 into 10 to the power of 3 Newton per mm square, by length is 200, right? And this is what you have, a 1 minus 1 minus 1, 1. On simplification, this value will come, that is 3.5 into 10 to the power of 5. So 3.5 I'll multiply, and 10 to the power 5 I'll take common, right? So it is what? 3.5 plus minus 3.5 minus 3.5, and this is the 3.5. So this is your K2, right? Now we need to means we have to globalize them, means we have to add the stiffness 1 and stiffness 2, right? So then we'll find out the global stiffness matrix. So for that we should add this K1 and K2. So next step we have it, that is step 3, right? Step 3. So step 3 means what? Global stiffness matrix. So global stiffness matrix, right? Global stiffness matrix. Okay, so global stiffness matrix, how we will get that? K is equal to K1 plus K2. Simply you have to add this. So before adding, I will show you that how the element are connected, right? So this is the finite element model we have taken in a step 1, that is node 1 node 2, means element 1 is connected between node 1 and node 2, and similarly the element 2 is connected between 2 and 3. So if, as we have finded the stiffness matrix here, so this is your U1, is it or not? And this is the U2 row, and this is the U1 and U2 column, right? Similarly for element 2, how it is connected? The element 2 is connected between 2 and 3. So we can write the nodal displacement here, that is U2 and U3, and this is what you have, a U2 and U3, right? So the size of the matrix, the global size of the matrix, for the global size of the global matrix is 3:3. Why? Because node is 3, right? How many node is there? The size of the matrix will be same. So here the nodes, 3 nodes is in the given problem. So the size of the matrix will be 3:3. So we will find out the 3:3 matrix by addition of K1 and K2. So here you have a, let's say it is U1, U2 and U3. This is column 1, column 2, column 3. U1 row 1, U2 row 2 and U3, that is row 3, right? Similarly you can add that, you'll see where is the U11. So U1 is 18.75. We don't have any 1 in element 2, so it is, and 10 to the power 5 we have taken common. Why? Because it is common in every, means in both the matrix. So it is 18.75, right? Next element is what? U2 U1, right? So we'll see where the U2 U1. So we have a U2, right, and U1, that is minus 18.75. Similarly we will check Whether we have a u2, u1 in this matrix? No. So that same value we will write. That is what? 8 minus 18.75. We'll see the u3, u1. Do we have u3, u1 in the matrix 1? No. We have a 1, 2, 1, 2. In this we'll check. We don't have 1, 3. So 3, 1 is not there. It will be 0. Next element is what? u1, u2. Right? That is first column, second row. So first column, second row we will see. First column, see here. First column, second row, minus 18.71. Do we have first column, second row in the element 2? No. So it is minus 18.75. Right? Second is what? That is u2, u2. So we'll see the second row, second column. So second row, right? And second column, that is this 18.75. We'll check in the second element also. So second row and second column. Yes, in element 2 also we have a second row, second column. So these two value will add, means 18.75 and 3.5. It will become 22.25, right? So this is what 22.25. We'll see for the u3, u2. u3, u2, do we have in the element 1? No. Third row, second column is not there. So u3, u2, that is third column, second row, minus 3.5. Minus 3.5. Then we'll see 1, 3. 1, 3 we don't have, that is 0. 2, 3. We have a 2, 3, that is this second column and third row, that is minus 3.5. And 3, 3 is finally 3.5. So this is how we will add the matrix. Right? After addition, this is your finite element global stiffness matrix. You can write it here, that is K is equal to this. Or, okay, in fresh, you can write that K is equal to 10 to the power of 5, 18.75, minus 18.75, 0, minus 18.75, 22.25, minus 3.5, 0, minus 3.5 and 3.5. Okay, so this is what we got the global stiffness matrix. Now we'll move to the step 4, that is finite element equation we will see. Right? So step 4 you have step 4, right? That is the finite element equation, right? Finite element equation. So what is the finite element equation? That Q is equal to F. K is the global stiffness, Q is the load nodal displacement, and F is the load vector, right? So here for understanding purpose you can write this is the global stiffness matrix, right? Global stiffness matrix, right? This is the nodal displacement. That nodal displacement we have written at the starting, finite element nodal displacement. Sorry, this is the nodal displacement. And this is the global load vector. Global load vector. Alright. Then we will see the K we already calculated. Q you know that is U1, U2, U3. And F is the F1, F2, F3. So we will formalize this value into that equation, right? So we will see first K is equal to what? K is equal to 10 to the power of 5 of whatever the K we have calculated, 18.75 minus 18.75, right? It is 0 minus 18.75. This is 22.25 minus 3.5, 0 minus 3.5 and 3.5. This is the K, right? That is just this K we have written. Beside that, we will write down the nodal displacement. What are the nodal displacement you have? U1, U2 and U3. Okay, is equal to F1, F2, F3. So we will write, here we have a F1, F2 and F3. We'll check whether the load is given in the element or not. So we have a question is here, that is, this is what the question is given. At node 1 we don't have any load. At node 2 60 kilonewton load is acting towards right. As it is right, it will be positive. At node 3 we don't have any load. So at node 1 and node 3 the load we will mention 0. At node 2 we will write down the 60 kilonewton. Right. So here, that is F1 is equal to 0, F2 is equal to 60 into 10 to the power of 3, that is Newton. Kilonewton is there, so that's why we have multiplied 1000 and it is 0. This is what you have a finite element equation. Now this equation we have to find out the nodal displacement, right? So again this problem can be solved by elimination approach. Elimination approach means what? That we need to impose the boundary condition. We have to check at what point the nodes are fixed. The point where the nodes are fixed, at that point we don't have any nodal displacement, so we will take it at 0. Okay, so we have, again we'll go through the problems. The problem is here, that is, you can see that node 1 and node 3 are fixed. It means that u1 and u3 will be 0. Why? Because as it is fixed, so when the load is act on the element, there is no displacement along at the node 1. Similarly, there is no displacement at node 3, right? So at node 2 we have a displacement, we have to find out that. So it means that u1 and u3 will be 0. So as the boundary condition is u1 u3 will be 0, so here you can say applying boundary condition. Applying boundary condition, right? Applying boundary condition. So boundary condition is what? u1 is equal to u3 is equal to 0, means first. Then when you impose this elimination approach, this problem we are solving now by elimination approach. Elimination approach means what? The node where the element are fixed, at that point the nodal displacement will be 0. So particular nodes for particular nodal displacement, that row and column will be eliminated. So u1 is 0, it means that the first row and first column will be eliminated. Similarly u3 is 0, so third row and third column will be eliminated. So now we can apply the elimination approach, that is u1 first row and first column. Similarly, third row and third column is eliminated. So purpose of elimination is that we have to reduce the size of the matrix. Actually the matrix size is 3:3. After elimination the matrix size is 1:1, right? Why? Because only one element is left out. So now we can solve this problem. So the next, so here the element is become like that. After elimination, you can say after elimination, right? How it become? This is 10 to the power 5 is there, and only the element which is left out 22.25 into u2 is equal to f2, that is 60 into 10 to the power of 3. I will show you again. That is, see here how we have eliminated. So we have eliminated this first row, first column, third row, third column. So only this element is left out, which is 22.25, and the u2 and this particular 60 into 10 to the power of 3 Newton. So we can simplify this and we'll get the nodal displacement at 2. So here you can say u2 is equal to, on simplification, simply u2 is equal to what? 60 into 10 to the power 3 by 10, 22.25 into 10 to the power of 5. So it will be 0.026 millimeter. Right? So you can write, therefore, the displacement field, right, that u is equal to u1 U2, U3 is equal to what? Is equal to U1 is 0, U2 you have calculated, which is 0.026, and U3 is also 0. So this is your answer, right? Next we will find out the stresses in each bar, right? So second means this is A part is completed. The B part is stresses in each bar, right? Stresses in each bar. So stress is load by area. That formula we won't use. We'll use the finite element equation, that is sigma 1 stresses in bar 1 is equal to, we have a E1 by L1, right, minus 1 1, and the nodal displacement you have a U1 and U2. Why? Because this element 1 is associated with the node 1 and node 2, right? This is node 1 and node 2, that's why we are taking U1 and U2. While you find out the stress 2, then you have to take U2 and U3. So here we have a E1 is what is that, 150. Let me check. Sorry, this is 200 right now. This is the 200 into 10 to the power of 3 by L1 is 200. It is minus 1 1. U1 is 0. U2 you have calculated 0.026, right? So I will show you how you get this. That is, this is 200 200 get cancelled, so it is 1000 10 to the power 3, and this row will multiply with this column, right? So it is what, minus 1 into 0 plus 1 into 0.026, right? So it is 0, it means 0.026, so 1000, right? So it will how much? When you multiply with 0.026 into 1000, 26,000, and then this is the 260, 26 I think. Let me check, wait, that is 0.026. Yes, this is the 26, right, MPa, that is mega Pascal, Newton per mm square actually it came, so it is same as a mega Pascal, right? So this is your stress in element 1. Similarly, we will find out the stress in element 2, right? So now you can write, that is a stress in element 2, right? So what is that stress? Sigma 2 is equal to E2 by L2 minus 1 1, and this is connected between 2 and 3. So this is U2 and U3, right? So E2 is what? 70 into 10 to the power of 3 by L is 200 minus 1 1, and U2 is 0.026 and U3 is 0, right? So similarly you can find that is this, some value will be there, some value I mean to say that is 70 into 1000 by 200. This is 350, and this is minus 1 into 0.026 plus 1 into 0, right? So this is what you have a 0.026 into 350. So answer into, sorry, 0.026 into 350. So it is 9.1, right? So this will be the 9.1 megapascal. This is sigma 2. So stress 1 and stress 2 in each member we calculated. The last one we have to calculate the reaction, right? So the last, finally we have to calculate the reaction. So how we calculate the reaction, I will show you here, that the reaction you need to find. So reaction, for finding the reaction, we will write down this same equation, that is whatever the finite element equation we have written, KQ is equal to F. Same equation we will find, right? But we have to find out the reaction at a point where, wait, that reaction they are asking the, find out the reaction at the support. So where is the support? Support is this one and this one, means R1 and R2 you have to find. Reaction we are denoting by R1 and R2, right? So here and here you have to find. Here you don't have to find out the reaction, load is given. A reaction is nothing but the actions, right? Opposite of the action is the reaction. So here our action is what? 60 kilonewton. So same reaction will act in opposite direction, but here we don't have any action is given. So you need to find out the reaction at that point and at that point. Means you have to remember the reaction we will find at that node where the load is not given. Okay. So this is what you have to find out the R1 and R2. For finding the reaction, again you have to write down this equation, but in place of F1 we will write R1 and in place of F3 we will write down the R2, right? And here we will write same, that is 60 into 10 to the power of 3. So now you can say reaction means that reaction at each support, right? So how you will write that? First of all, finite element equation we will write 10 to the power of 5 and the K is 18.75 minus 18.75. okay, this is 0 and it is minus 18.75, 22.25. this will be minus 3.5, this is 0, minus 3.5 and 3.5. K we have written. Then we will write down the U1, U2, U3. U1 is what? 0. U2 we calculated 0.026 value we are writing, and U3 is 0. We have to find out the reaction R1 first at each support. R1 at support 1, R2 is given, that is 60 into 10 to the power of 3 is not required to find, and R3, right? Okay, so for R1, what is that? Simply you have to take this whole row with this column, right? So means what? That means 10 to the power of 5 will take common, and this is what? 18.75 into 0 plus, right? And this is what? Minus 18.75 into 0.026. this into this, again this into this, plus 0 into 0. This is equal to R1. So you can simplify and get that answer. That is R1 is equal to what? Let me check. I'll show you that here 18.75 into 0, right? This plus and minus will become minus, so I'm writing minus only. 18.75 into 0.026, right? Again plus 0 into 0. It is came like this, 0.4875 minus it's coming, and 10 to the power 5 is multiplied. Answer into 10 to the power of 5. Alright, so it is this 48.75 into 10 to the power of 3 Newton. So on simplification you will get minus 48.75 into 10 to the power of 3 Newton. Minus sign means the reaction is acting towards left. Similarly, you can find out the R3, right? For this R3, what you will do? Take the third row and this column will give you the R3. So what is that? R3 is equal to 10 to the power of 5 is common, and the remaining is what? 0 into 0. That means this into this plus this into this. So plus is there, it minus, this is minus, actually plus, so plus minus will minus, right? So minus 3.5 into 0.026 plus 3.5 into 0. So is it or not? Minus 3.5 into this plus 3.5 into 0. So on simplification, R3 is equal to, you have a let me check, (9.1) into 10 to the power of 3. 9.1 into 10 to the power of 3 Newton, right? So this is how we will solve the problem for finite element methods for one-dimensional bar element. In subsequent classes, we will solve the problem which is related to the truss, beam and heat transfer. So please do like, subscribe, comment and share this channel. Thank you.